All right, and here's our next topic. This is part of C3, C4, expectations and vectors. So we're talking about equations of lines. So equations of lines in two space, we're just gonna focus on two space right now. So we've seen these before. This is a standard form equation, and we've seen slope-intercept form. We've used them in grade 9, 10, 11, 12. So we're now going to refer to this equation right here, ax plus b. Instead of calling it standard form, we're actually going to call it a scalar equation of a line. So we're going to call this the scalar equation of a line. Okay, that's what we're now going to refer to it as. Not standard form, but a scalar equation. And we are going to learn, today's video is, we're going to learn how to change a scalar equation into a vector equation. So this is a little bit of a confusing explanation here. So let's do it with an example to start off with. So here we have a scalar equation of a line. And I sketched it out. I found out the y-intercept was 5 and the slope was a half. So I just sketched it. So if I want to write the vector equation of it, it turns out the vector equation is written using addition of two vectors. So R naught is a position vector that goes from the origin to any point on the line. Doesn't matter where it goes, it just goes to any point on the line. So you should be able to tell that there's not one unique vector equation for one specific line. There could be multiple because there's a lot of different position vectors you could get. So for example, for this one, our position vector could be the vector 2, 6. So 1, 2, 1, 2, 3, 4, 5, 6. So this point right here, so R naught could be, so if I'm writing a vector equation, I could use the position vector as vector 2, 6. There's lots of position vectors though. It doesn't matter which one you pick. Okay, then we have to add vector S, which we're actually not going to call it vector S. I'm just calling it like that for now while I explain this. So we're going to say vector S is some vector that starts here and goes however far. Doesn't actually matter. So let's say that's vector S. And then, so plus, so we'll say vector S is like 1, 2, 3, 4, 1, 2. Vector S is like the vector 4, 2, right? Sorry. Ugh. So I'm going to say 4, 2. And then, so if I add those two vectors together, what I end up with is, so I'll call this R naught, S, and this is vector R. So that's how I write the vector equation of a line, but not exactly. So it's written like this is how you do a vector equation, but so you know how we were talking about like the vectors could be, I'm explaining this poorly. I could have made vector S only this long, right? And then that could have been vector R. So like there's different ways I could have written this. So because of that, we're actually going to use a parameter, which is just a variable that can represent anything, to help me write a better equation. So instead of this S vector, we're going to actually change that to, we're going to call it a direction vector. So I'm going to use an M to represent it instead. So this is going to be, this is our position vector. I should write this down. So that's a position vector. So it goes from the origin to a point on the line. And this is so I'll just say it's a point on the line. Point on line. And I'll call this the direction vector. So So this vector has to be a vector that's parallel to the line. So my vector, whatever it was, 4, 2, it's a vector that's parallel to the line. So that is a vector. Or I could have used like a smaller one. I could have used the vector 2, 1. Right? So I also could use the vector 2, 1. So I tend to use the smallest one. I don't think it has to be. It just has to be a vector that's parallel to the line. You could have used 4, 2, 2, 1, whatever you want. So let's say I used the vector 2, 1. So it's a vector that's parallel. So I'm going to say that's vector M. Now I'm going to use a parameter. I'm going to use the parameter t. So I'm actually going to put a t in my equation. T is just any real number. It's like scalar multiplication of this direction vector. And that's how you write the vector equation of a line. Yeah. So I guess by changing the value of the parameter, like you can get to any point on this line by changing the parameter t. Because it doesn't matter how long the direction vector is. Like once you apply some kind of scalar multiple to it, it's still going to always be parallel to our line. And that is confusing, but that is how you write a vector equation of any line. So what you need to know is, you need to know a point on the line, right? Like that's how we get our position vector. We have to know one point on our line. We also have to know a vector that's parallel to our line. And those are the only two things you need to know to write the vector equation of a line in 2-space. So let's just try one question. All right, let's say we have, let me give you some points. So say we have the point A, which is at 1, 4, and we have a point B, which is at the point 3, 1. And I want to write the vector equation of a line that goes through these points. Okay, cool. So right now I just have 2 points and I want to write a vector equation of them. Cool. So I think first I will get a vector from them. How about to get my direction vector? So, step 1, I think I'm going to get my direction vector. Because I already know a point on my line, so I already have a position vector. So I need to get a direction vector. And I might as well get it by using the vector AB. So I'm just going to subtract my points to get that. So 3 minus 1 is 2, and 1 minus 4 is negative 3. So that's like my direction vector. And let me just sketch that out in case you're having trouble understanding that. So I've got this point 1, 4, 2, 3, 4, and I've got this point 3, 1. So that's A, B. And I'm trying to find the equation of a line that goes through those 2 points. So I need a direction vector that's parallel. So I came up with the vector 2, negative 3. 1, 2, 1, 2, 3. And we can see that it's actually parallel to that line. See, it's like 1, 2, 3, 1, 2. It's totally parallel to that line. So finding vector, what I did was I found vector AB. I found the vector from point A to point B. And that's like finding a direction vector. It's parallel to our line. Okay, so I've got a direction vector. The other thing I needed was R0, which is a position vector. And remember I said above here, it's like a point on the line. So I could use either of those points. So I could use A, 1, 4. Because the vector 1, 4 would be, let me just get rid of that. The vector 1, 4 would be 1, 1, 2, 3, 4. It would be this vector. So it's pointing right to a point on my line. So that's all I need, a direction vector and a point on the line. And then I can write the vector equation of my line, which I'm going to write as, you can either start it with R equals, or you can start it with X, Y equals. Those are both acceptable notations. So I could say xy equals, I could use a point like 1, 4, plus, I need a parameter, so I always use t, and then my direction vector, 2, negative 3. Or you could have done the same thing using r at the beginning of the line. Doesn't matter. Those are just the acceptable notations for writing. So these are called the vector equations. So instead of writing a scalar equation, like a scalar equation using the slope and the y-intercept, we can write a vector equation using a direction vector and a position vector and a parameter. And that's how you write the vector equation of a line. And I wasn't going to do this, but since I had to re-record this video, there's actually, you can take it one step farther, and you can actually split up vector equations into what's called a parametric equation. And I thought I would just talk about it now because parametric equations are not that difficult. Parametric equations just split a vector equation into the x and the y component. So this parametric equation would actually be equal to x equals, so the x components are 1 and 2. 1 plus 2, and I have to include the parameter, t. And then my y is equal to 4 plus negative 3t, or 4 minus 3t. So vector equations are the whole thing right here, like I just showed you. And then there's something called a parametric equation. And a parametric equation just splits it into its x and y components. So there you go. That's how you do a vector and a parametric equation. I'm just going to keep going. You can stop it though. I just thought, you know what? I better do an example from a scalar equation. Oh my gosh, it's going to be way longer than I said. Okay, say we have this, which we now call a scalar equation. We no longer call it standard form. Hey, you scalar equation, I am going to turn you into a vector equation. So I'm going to turn this scalar equation into a vector equation. All right, so I need a point on the line, and I need a direction vector. Okay, cool. So how can I find a point on the line? I guess I could just sub stuff in, right? Like I could use an intercept. Like let's just pretend I subbed in 0 for y. So I'm going to find a point on the line. So if I just sub in 0 for y, what would x be? Okay, so 5 times 0 is 0. 4x equals negative 20. Divide by 4. Negative 5. I think that works. So all I did was I just subbed in 0. You could literally sub in any number you want. I just thought 0 would be easy. And then I just isolated x. So there's an infinite number of points on a line, right? You can pick any of them. Negative 5, yeah. So I'm going to use the y-intercept as my position vector. Why not? Okay, so I got my position vector. Check. Now I need a direction vector. So I need to use my scalar equation to get a direction vector. And so I can do this in a couple ways. I could find 2 points on my line and get a direction vector from those 2 points. So let's say I do that way. So I already know 1 point on my line. I could actually get the y-intercept too if I wanted to. So I'll just sub 0 in for x. It just seems like an easy way to do it. So 5y equals negative 20. So y would equal negative 4. So another point on my line is the point 0, negative 4. So now I know 2 points. Now I could get a direction vector, right? Because if we have 2 points on a line, you can easily get their direction vector. Okay, so a direction vector, what was I calling that? M would be like, I just subtract the x's and subtract the y's. Okay, cool, I can do that. So 0 minus negative 5 would be 5. Negative 4 minus 0 would be negative 4. Okay, so now I have a direction vector and a point, so I can write a vector equation. xy equals, I pick one of my points, doesn't matter which one, negative 5, 0, plus a parameter, and my direction vector, 5, negative 4. Do you guys notice that there's a connection between those coefficients there? 4, 5, 5, negative 4. Let's see if that happened before my other example. My other example, I had a coefficient of 1 and negative 2, and my vector was 2, 1. Interesting. Okay, and I could find the parametric equations of that if I wanted to as well. But I'm not going to.